This videotape deals with trig functions of some basic angles and graphs of the sine and cosine functions. It would be helpful to know the trig functions for some basic angles, and that's what we're going to try to start off doing. We're going to develop sines and work out sines and cosines for certain basic angles. Now, you might wonder, what do we mean by a basic angle? Well, let me start by saying 45 degrees is one of the basic angles that we consider, because we can think of 45 degrees in the following way. We can get a 45-degree angle by considering an isosceles right triangle. If you remember, a right triangle is one that has a right angle in it, and an isosceles triangle is one in which the base angle has two equal sides and the base angles are equal. So an isosceles right triangle would have to have a right angle and two equal sides. Okay, now the base angles here, well, these two angles, the two angles opposite the equal sides would also be equal. And if a triangle has only 180 degrees, the sum of the three angles in a triangle is 180 degrees, and 90 degrees is taken up by the right angle, that leaves us with 90 degrees to be split between these two angles here. And since they're equal, this gives us 45 degrees for this angle and 45 degrees for this angle. Okay, so we see that 45-degree angle comes in very nicely as part of an isosceles right triangle. Isosceles right triangle. Okay, if you would like to think of, let's say that this isosceles right triangle had legs of length 1 foot or 1 unit, whatever you want to call it. This is 1 unit, and this has length 1 unit. Then you could figure out what the hypotenuse is. Let's call it temporarily x. Using the Pythagorean Theorem, 1 squared plus 1 squared must be equal to x squared. A squared plus b squared equals c squared. The square of the hypotenuse is equal to the sum of the squares of the two legs, giving us that 1 plus 1, or 2, is equal to x squared, or x must be equal to the square root of 2. Okay, the length of the hypotenuse, of course, is not negative, so it must be positive square root of 2. Although x squared equals 2 has two solutions, x is plus or minus the square root of 2, we're only interested in plus the square root of 2. Okay, so the hypotenuse of this triangle has length the square root of 2 units. If this is 1 unit and 1 unit, then the hypotenuse is the square root of 2 units. Square root of 2 is approximately 1.4. Okay, something like that. Now, from this, we can write down the sine, cosine, and tangent of 45 degrees. I'm going to be using our SOHCAHTOA definitions here. They're the most convenient to work with. Sine, if you remember, in a right triangle like this, sine is the length of the side opposite the angle divided by the length of the hypotenuse. Cosine is adjacent over hypotenuse, tangent opposite over adjacent. So for the sine of 45 degrees, we have the length of the side opposite 45 degrees, which is 1, over the hypotenuse, which is the square root of 2. For cosine, we have adjacent over hypotenuse. I'm using, by the way, this angle, although I could have used this one. It's also 45 degrees. For cosine, I have adjacent over hypotenuse. The length of the side adjacent is 1 over the length of the hypotenuse, square root of 2. Tangent is opposite over adjacent, 1 over 1, or just 1. Alternately, you could have found out the tangent of 45 degrees is 1 by saying tangent of 45 degrees is sine of 45 degrees over cosine of 45 degrees. 1 over the square root of 2 divided by 1 over the square root of 2, of course, would just be 1. By the way, sometimes we write this in a slightly different form. We can rationalize the denominator here. You know that we can multiply a fraction. The numerator, you can always multiply a fraction by 1. And we will multiply, in this case, the numerator and denominator by the square root of 2, giving us 1 times the square root of 2, or the square root of 2 on top. On the bottom, the square root of 2 times the square root of 2, which is just 2. And similarly, 1 over the square root of 2 here can be written as the square root of 2 over 2. Either way, it can be worked out. Either 1 over the square root of 2 for the sine of 45 degrees, or the square root of 2 over 2. So we have the sine, the cosine, and tangent of 45 degrees. By the way, a 45-degree angle, okay, we can work out the radian measure of such an angle. If you'll remember, to get the radian measure of an angle, we would take the degree measure and we would multiply by pi over 180 degrees. Okay, if we do that, if you multiply by pi over 180 degrees, we get 45 degrees into 180 degrees goes 4 times. This is pi over 4. So either a 45-degree angle or an angle of pi over 4 radians. Okay? An angle whose degree measure is 45 is equivalent to an angle whose radian measure is pi over 4. So we can use those interchangeably. Okay, now let's look at some other basic angles. In this sense, we can think of basic angles arising very nicely in some geometric situation, as this isosceles right triangle gave rise to 45-degree angles. Okay, right now we're going to work with 30-degree and 60-degree angles. And once again, we can start off with a nice geometric picture. Let's work with an equilateral triangle. One that has all 3 sides equal in length. Okay, let's start with an equilateral triangle. And let's say each of the 3 sides has length 2 units. 2, 2, and 2. An equilateral triangle is also equiangular. It's 180 degrees to be split equally among the 3 angles, giving us 60 degrees in each of these angles. Furthermore, it is also true that in an equilateral triangle, if we were to say from this vertex, draw an altitude here to the base. In an equilateral triangle, this altitude to the base is also the median, which means it bisects the base, and it's also an angle bisector. The altitude, the median, and the angle bisector are all the same line segment. Okay, now, if it's an angle bisector, it must cut the 60-degree angle into 2 equal 30-degree angles. And furthermore, it must cut this base of length 2 into 2 segments, each having length 1. Okay. Now, by the way, this is not true in all triangles. Let's say we had a triangle that looks something like this. You will notice that the altitude clearly is not a median to the space here. This altitude does not bisect the base. But in an equilateral triangle, it does. Okay, let us clear up this picture a little bit. Let us just say copy down the triangle on the left. Let's see what we have. We have the right angle from here. We have a 30-degree angle here, because it's half of the 60-degree angle. We have a 60-degree angle here from the original 60-degree angles of the equilateral triangle. This hypotenuse is one of the original sides of the equilateral triangle. It has length 2. And this base here must have length 1, since it is half of the entire base of this triangle, which had length 2. We have here a 30, 60, 90-degree triangle. And from this, of course, we can get information about the sine and the cosine of 30 degrees and 60 degrees. These are also known as basic angles. Now, first, in order to do that, I would like to stop off and figure out the length of this side of the triangle. Let's call the length of this side, let's say it's A. Using the Pythagorean Theorem, 1 squared plus A squared must be equal to 2 squared, or 1 plus A squared must be equal to 4. A squared, therefore, must be equal to 3. And taking for A the positive square root of 3, okay, not the negative square root because it represents the length of a side, we have here now that this side of the triangle must be equal to the square root of 3. Since we know all the sides and we have the angles labeled, from this triangle we'll be able to read off the trig functions for 30 degrees and 60 degrees. Let's do that. We want the sine of 30 degrees the cosine of 30 degrees, the sine of 60 degrees, and the cosine of 60 degrees. All right. Remembering sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. We could also figure out the tangent of 30 degrees and 60 degrees, but I find it simplest just remember that the tangent of an angle is the sine of the angle over the cosine of the angle. Okay, and instead of remembering tangents, just remember my sines and cosines and know that I can always divide to get a tangent. Okay, sine of 30 degrees. Here's a 30-degree angle. Sine is opposite over hypotenuse. The side opposite 30 degrees has length 1. The hypotenuse has length 2. So sine of 30 degrees opposite over hypotenuse is 1/2. Okay, cosine of 30 degrees adjacent over hypotenuse. The side adjacent to 30-degree angle is has length square root of 3. The hypotenuse is 2. Now we switch our orientation. We're now down here, 60-degree angle. The sine of 60 degrees is opposite over hypotenuse, but the side opposite 60 degrees is this side of length the square root of 3. And the hypotenuse is 2. And the cosine of 60 degrees adjacent over hypotenuse is 1/2, 1 over 2. Notice that the sine of 30 degrees is equal to the cosine of 60 degrees, which is not too surprising because in an earlier videotape we learned that the sine of an angle is equal to the cosine of its complement. And similarly here, the cosine of 30 degrees is equal to the sine of 60 degrees. The sine of this angle is equal to the cosine of its complement, or the cosine of this angle is equal to the sine of its complement. Okay. By the way, we can get the equivalent, the radian measure equivalence of these angles. A 30-degree angle, if you were to multiply by pi over 180 degrees, you see is equivalent to an angle whose radian measure is pi over 6. And a 60-degree angle, if you multiply by pi over 180 degrees, is equivalent to an angle whose radian measure is pi over 3. Okay, what I would like to do now, just for future reference, later on in this videotape, just to record what we have so far. We have for 30 degrees, 45 degrees, and 60 degrees. We have the sine of the angle and the cosine of the angle. Later on in this tape, I'll show you a neat way of remembering these values. Right now, I just want to accumulate these values so that we'll have them later on. Okay, for 30 degrees, we just worked this out. The sine of 30 degrees is 1/2. The cosine of 30 degrees is the square root of 3 over 2. For 45 degrees, let's go back over here for a moment. Remember when we had the 45 degree, 90 degree right triangle? The sine of 45 degrees was equal to the cosine of 45 degrees. Both of them were the square root of 2 over 2. Notice that the sine and the cosine came out the same. Of course, it must be true this way because these two sides had the same length. So sine, which was opposite over hypotenuse, came out the same as cosine, which was adjacent over hypotenuse. Okay, and they were each the square root of 2 over 2. Let's put that into our chart. Sine and cosine 45 degrees is the square root of 2 over 2. And finally, for 60 degrees, the sine of 60 degrees is the square root of 3 over 2. And the cosine of 60 degrees is 1/2. And we'll be coming back to this. Okay, what I would like to do now is work out the trig functions for some angles other than 30, 45, and 60 degrees, some of the so-called quadrant angles. By the quadrant angles, I mean 0 degrees, 90 degrees, 180 degrees, 270 degrees. I call these quadrant angles because if you draw your coordinate axes, fix up that x-axis a little bit. If you think of angles having their initial side on the positive x-axis, at a 0-degree angle would have its terminal side also along the positive x-axis. A 90-degree angle would have its terminal side along the positive y-axis. A 180-degree angle would have its terminal side along the negative x-axis, and 270-degree angle would have its terminal side along the negative y-axis on the quadrant, on the lines, the x and y axes, which separate the quadrants. Okay. Now, when you're dealing with angles other than acute angles, okay, the SOHCAHTOA definitions are not good for us anymore. You remember this was the original reason for defining the trig functions for angles of any size. And recalling how we did this, by the way, if you haven't seen the videotape, I would suggest you go back and look at the videotape, which is, I think, entitled Definitions of the Trig Functions. Okay? Those of you who have seen it, the idea was that an angle of any size is put in standard position, that it has its positive, the initial side along the positive x-axis, and its terminal side can be anywhere. Let's say, for the sake of argument, it's somewhere in the first quadrant. This is an angle theta. And what we do is we choose any point on the terminal side of that angle, let's say point P, where the distance from this point P to the origin we denote by R. R represents the distance from P to the origin. And we then define trig functions of this angle theta. In particular, we're interested here in the sine and the cosine. The sine of angle theta is defined to be the y-coordinate of this point on the terminal side divided by r, the distance of this point from the origin. And the cosine of angle theta is defined to be the x-coordinate of this point divided by its distance from the origin. Okay, now these are equivalent to the SOHCAHTOA definitions if the angle is in the first quadrant. All you would have to do to see that is to drop a perpendicular to the x-axis, finish off a right triangle. This leg of the right triangle would have length x, this length would have length y, and you see that y over r is equivalent to opposite over hypotenuse. The advantage to this type of definition is that it's applicable in all quadrants. Okay, it does not have, you don't have to be restricted to an angle in the first quadrant. Okay. Now we're going to get the trig functions for 0, 90 degrees, 180 degrees, and 270 degrees. A convenient way of doing this is to consider a circle that has radius 1. Okay, centered at the origin, draw one in, and for the sake of argument, let me assume that here, the way I drew it, that r was equal to 1. Remember, I could pick P to be any point on the terminal side of this angle. Let's say that I chose a point that was 1 unit away from the origin, like 1 foot, whatever, 1 unit here. Okay? Here we have a unit circle, a circle centered at the origin of radius 1. Okay, now if that r is equal to 1, this tells me that in this case, for this picture, sine of theta, which is y over r, is just y over 1, because r is equal to 1. Cosine of theta, which is x over r, is x over 1, or just x. Which means that as this point P, okay, say spins around this circumference of this circle, x comma y could be thought of as cosine theta comma sine theta. Cos theta comma sine theta. In other words, we could have any angle theta. P is a point on the terminal side of the angle chosen to be 1 unit away from the origin. Okay? The coordinates of point P are x comma y. But from here we see that if r is equal to 1, x is equal to cosine theta and y is equal to sine theta. In other words, as theta, okay, changes, we start with, say, an angle theta equal to 0, and then here theta is 90 degrees, 180 degrees, and so on. As theta changes, this point P on the terminal side is spinning around the circumference of the circle, and every time it reaches a point, the x-coordinate gives you the cosine of angle theta, and the y-coordinate gives you the sine of angle theta. Now, if this is a unit circle, it may not look like one, but if it is a unit circle, then clearly this must be the point 1, 0. This must be the point 0, 1. This must be the point minus 1, 0. And this must be the point 0, minus 1. Okay? It's a circle centered at the origin, radius 1. Okay, so this point is 1 unit to the right. The x-coordinate is 1. The y-coordinate is 0 because it's on the x-axis. Here and here, the x-coordinates are 0. And we go 1 unit up, 1 unit down. Here, the y-coordinate is 0. X is equal to minus 1. Okay, from this, we'll be able to read off right away the sines and cosines of these angles. Because when we're talking about an angle of 0 degrees, that means point P is right over here. The initial side and the terminal side of the angle coincide. Point P is a point on the terminal side, and we're choosing it to be a point whose distance from the origin is 1, so point P must be 1, 0. So the x-coordinate must be the cosine of 0 degrees, and the y-coordinate must be the sine of 0 degrees. Similarly, when theta is 90 degrees, point P is up here. The x-coordinate giving us the cosine of 90 degrees and the y-coordinate giving the sine. Here, when point P is here, the angle theta is 180 degrees, and when point P is down here, the angle theta is 270 degrees. Let's accumulate these values in chart form. If theta is 0 degrees, 90 degrees, 180 degrees, or 270 degrees. Okay. We could also put 360 degrees, by the way, down here. For 360 degrees, of course, theta is back here. Point P is back here at 1, 0, and the angle trig functions for 360 degrees are the same as those for 0 degrees. In this way, you can see that the trig functions are periodic in nature. They will repeat. In other words, you go from 0 to 360 degrees. 360 degrees, point P is back here. And from 360 degrees to 720 degrees, you're going to be repeating the values that you obtained between 0 and 360 degrees. Okay, so we say that the trig functions, sine theta, cosine theta, are periodic functions. And they repeat every 360 degrees or every 2 pi radians. Speaking of radians, let's write down the radian equivalents of these angles. Okay, you might want to try doing that on your own right now. Remember, you multiply by pi over 180 degrees to get the radian equivalents. Okay. Multiplying by pi over 180 degrees, of course, still leaves us with 0. The radian measure for an angle whose degree measure is 0 is also 0. Multiplying by pi over 180 degrees here leaves us with pi over 2. Multiplying by pi over 180 degrees here leaves us with pi radians, being equivalent to an angle of 180 degrees. Multiplying by pi over 2 here leaves us with 3/2 pi. And multiplying by pi over 180 degrees here leaves us with 2 pi. Now, to get the sines and the cosines of these angles, as I mentioned, all we have to do is follow this point P around the circle, okay, and taking its x-coordinate as the cosine and its y-coordinate as the sine. Okay, so let's take care of the cosines first. For 0 degrees, point P is here, and the cosine of 0 degrees must be 1. For 90 degrees, point P is here, and the cosine of 90 degrees must be 0, the x-coordinate of the point in each case. For 180 degrees, the cosine is -1. For 270 degrees, the cosine is 0. And for 360 degrees, we're back at the same place we were with 0. The cosine is 1. Let me write down those values for you. 1, 0, -1, 0, and 1. Okay, we let P spin around the circle, and we took the x-coordinates of those points as the cosines. 1, 0, -1, 0, and 1. Okay, similarly for the sines of these angles, as we spin around the circle, the y-coordinates of these points represent their sines, the sines of the angle theta. At 0 degrees, point P is here. The sine is 0. At 90 degrees, the sine is 1. For 180 degrees, the sine is 0. For 270 degrees, the sine is -1. For 360 degrees, the sine is once again 0. Remember, we're taking the y-coordinates for the sines. And we get 0, 1, 0, -1, and 0. Okay, we could use this information to sketch the graph of the sine and cosine functions. This coupled with the fact that we know these functions are going to start repeating because of this nature, right? If you were larger than 360 degrees, you're going to spin around and take the same values that you did between 0 and 360 degrees. Similarly, if your angle was less than 0 degrees. Okay. Let's try to sketch. Let's just make some quick sketches of the graphs of these functions. I will sketch y equals sine x and y equals cosine x. Okay, now when I'm sketching the graphs of these functions, okay, I would like to sketch them on coordinate axes where x represents a real number and y represents a real number. And I'm going to be, therefore, using the radian measures for the angles, okay? I wouldn't know where to put, say, 90 degrees. Pi over 2 radians makes sense to me. Pi over 2 is a real number. If you think of pi, for the purpose of these sketches, let's think of pi about 3. Pi is really about 3.14 or something, but for the purpose of the sketch, think about pi as about 3. So x will be 0, about 3 halves, about 3, about 9 halves, or 4 1/2, about 6. And the y values will be the sines and the cosines that we found over here. Okay, so that's what I'm going to need. Notice also that the sines and the cosines of an angle always run between -1 and +1. This is because when you were spinning around that unit circle, okay, the sines and the cosines had to be the x's and the y coordinates of those points. Now, if they were on the unit circle, okay, the x coordinate had to be someplace between, okay, here's our unit circle. Okay, the radius was 1. The x coordinate always had to be someplace between -1 and 1. Therefore, the cosine had to be between -1 and 1. Similarly, the y coordinate had to be between -1 and +1. So the sine of an angle has to be between -1 and +1. Okay, so we know that we'll never have to go higher than +1 or lower than -1. Let's say this is 1 unit. And 1, 2, 3, 4, 5, 6. Same here. 1, 2, 3, 4, 5, 6. Okay. This is +1, this is -1. +1 and -1. Okay, x represents, say, the angles. You could have used theta. I'm just using x for the horizontal axis. X is representing the angles. We're going to start with 0, which is over here. We'll want pi over 2, which we said would be put about 3 halves or 1 1/2. So this will be pi over 2. And then pi will be about 3. And at 4 1/2, okay, 3 halves pi will put it about 4 1/2. Okay, if pi is about 3, this is about 9 halves, about 4.5, and 2 pi is at about 6. All right, and the same thing, we'll mark off these axes the same way. This is 0, this will be pi, this will be 2 pi, which is about 6, pi over 2, and 3 halves pi. And now we're ready to sketch the graphs of these functions. Let's start with the sine curve here. We're going to be using this column and this column. There is x and sine x, where x is measured in radians. Okay, 0, 0 is the first point we come to. Then pi over 2, comma 1, or 3 halves, say, comma 1. Then pi, comma 0, which is about somewhere near 3, 0. Then about 3 halves pi, comma minus 1, about 4.5, comma minus 1. 4.5, comma minus 1 is here. And 2 pi, comma 0. Okay, connecting these, okay, in a smooth fashion. Okay, we get the graph of y equals sine x between 0 and 2 pi. And as I mentioned, it keeps repeating this way and also in that direction. And it's just a portion between 0 and 2 pi. Let's do the same thing for y equals cosine x. Okay, now we'll be using this column here for the angles, but we'll be reading off of the cosine column. All right, so we'll have 0, comma 1 as our first point. Then we'll have pi over 2, comma 0. Then we'll have pi, comma minus 1. 3 halves pi, comma 0. And 2 pi, comma 1. Okay. And connecting these points in the following way. Okay, that's a picture of y equals cosine x between 0 and 2 pi. And it also repeats. You might notice that there's not much difference between the basic shapes of these curves. The only difference is that, say, the cosine curve is, say, starting up here at 0. Okay, it's sort of like a 90-degree shift, or pi over 2 shift from this curve here. It starts at the top of this hill, goes down, comes up, and of course continues, as this curve would also continue. Okay, so we have y equals sine x and y equals cosine x between 0 and 2 pi. Okay, now, the last thing I want to do on this tape is give you an easy way of remembering trig functions of these basic angles. Okay, you remember that earlier in this tape we accumulated the values for 30 degrees, 45 degrees, and 60 degrees. Okay, by the way, this is pi over 6, pi over 4, and pi over 3 in radian measure. And we now also know certain others, 0 degrees and 90 degrees in particular. Okay, there's a neat way for remembering 0 degrees, 90 degrees, 30 degrees, 45 degrees, and 60 degrees. On 180 degrees and 270 degrees, you're just sort of on your own. I find one of the most convenient ways is just to remember what the sine and cosine curves look like. If you can keep these pictures in your mind, okay, if you can keep the pictures of the sine and the cosine curve in your mind, you won't have much trouble. Okay, if you can remember that at 180 degrees it was 0 here, at 270 degrees it was minus 1 the sine, and so on. If you have the pictures in your mind, you'll probably be able to do all right on this. Okay, but as I said, a simple way for remembering the trig functions, at least for 0, 30, 45, 60, and 90 degrees, is the following. Zero degrees, 30 degrees.